Good afternoon, everyone. In the last video lecture, we have discussed the modeling of a turbine. So today, we will be looking at the generator load model. Okay. So let us complete this generator load model today. We have developed mathematical models and also control system models for speed governor, for turbine. And now, in this lecture, we will try to develop a mathematical model and a control system model for a generator combined with a load. Before going any further, as you know, since I'm considering only PF channel, I'm not going to consider this excitation. So input to my for generator, what are the inputs? One is delta PM, which is coming from the turbine. The other one is delta PD, change in the power demand. This is change in the mechanical input. This is change in the electrical output. Right. The difference of these two are going to affect your speed of your rotor, isn't it? So you need to understand what is the change in frequency. These are the outputs. Okay. So these two are the inputs and this is the outputs. Change in frequency. So you need to develop a mathematical model which gives you the magnitude of change in frequency, which is happening in the system due to a change in mechanical input or the demand. So now we will try to develop that one today. So moving ahead, assuming that the turbine is providing the generator with some mechanical inputs and there is a steady demand. So assuming that there is a steady state position of the rotor, such that it is rotating at some velocity and having some kinetic energy. Okay. So I am assuming that the rotor is initially running at a speed of omega naught with kinetic energy of K naught. With kinetic energy of K E naught. Okay. Where W K E naught, I'll write it as W K E naught. Okay. This is energy. This is kinetic energy of the machine, and this is the power which is used to give up this kinetic energy, which is the power which is involved to give this kinetic energy. Okay. Now, if say this is kinetic energy and this is power related to this kinetic energy. Now, any change in mechanical input, it is coming from turbine, right? Any change in the mechanical input which is coming from the turbine, isn't it? Or any change in load, which I'll represent as delta PD. This is, I'll represent it as delta PT or delta PM, whatever you want, you can choose it. Any change, either this is delta PM or delta PD, will result in change in frequency. This is the most important point which we are gonna consider, which we are gonna develop the mathematical model for this. Okay. So before moving further, before moving to develop a mathematical model for relating these three terms, 1, 2, and 3, first let us analyze what will happen actually in the system. Okay. So I'm considering delta PT, or you can choose it as delta PG also, because this is the mechanical power which is being, this is the mechanical power, or what you call it as the amount of power which is actually generated. And this is the demand. The difference between these two is going to affect your frequency. Okay. Now, the difference of these two this is counted as the difference between these two, delta PG and delta PT, is often referred as increment of power input to the generator load. Okay. This is equal to delta PG minus delta PD. This is the power which is actually being fed to your generator now. Okay. Now what will happen, I will show you. So let us suppose there is a motor, a generator, which is taking up delta PG, and it is giving some PM, assuming that it is a steady state. Now there is some small change, delta P, let us assume delta P, and the same value is happening here also. So what will happen? The system runs at steady state itself. The system runs it with its normal speed itself, right? But let us suppose it is higher, delta P square or 2 into delta P. See, this value is higher when compared to this one. What happens? Since there is a more amount of energy which is being fed to your rotor, the system, the rotor accelerates. So when it is happening, when there is a difference in the change in mechanical power, or this delta PG and delta PD, this is delta PD. When there is a difference in the changes in this one and this one, then automatically the rest is going to act as an input to your rotor. Okay, that is what I have mentioned here. The increment of power input to the generator load model. I am assuming that this is the generator load model. This is equal to delta PG minus delta PD. Okay. Now, this particular increment of power input, this is accounted in two ways. This is accounted in two ways in general. So, what are the two ways in which this particular power input is accounted for? That we are going to see now. First, let us go with the first one. Any change in this generation and the demand, as you all know, it is going to affect your rotor speed directly. So first of all, we will consider that point, that any difference between these two is going to affect my rotor. Okay. So now, first of all, I'm going to write down this one. This is a rate of frequency. Sorry. So what happens when there is so what is happening when there is an increase in power? Let us suppose if mechanical power is more given to your rotor than the demand. Then automatic development, the rotor accelerates, isn't it? The speed of the rotor is going to increase, which means that the kinetic energy is going to increase, isn't it? We are sure that kinetic energy is going to increase because there will be an increase in the speed. But here we should represent it in terms of power, not energy. So that's why there will be a change in kinetic energy, isn't it? There will be a change in kinetic energy. Whenever there is a change here, there will be a change in kinetic energy of the rotor. But since this is power, this is energy, what I will be writing is rate of change in kinetic energy of the rotor. Okay. So it states that whenever there is a change here, there will be a change in the rate of change in the kinetic energy of the rotor. Now, first of all, let us have a mathematical model for this one. At initial frequency, as already I have mentioned that, at initial frequency of F0, let static kinetic energy is equal to K, and the power is equal to P at K. Okay. Assuming that this is the kinetic energy at the frequency, initial frequency, K0, and this is power related to it. Okay. Normally, you know that kinetic energy is equal to H into PR, where H is called as the inertia constant. We will discuss this particular equation, kinetic energy is equal to H into PR, in the last unit. H is generally called as the inertia constant. PR is the power rating of the turbine generator in megawatts normally. Okay. So at initial frequency, F0 is equal to, let initial frequency be F0, and the kinetic energy at F0 is going to be K. Okay. So I can represent this one as okay. Now, yeah. Now, what is the frequency at this one? The frequency is going to be F0, isn't it? Now, you know that W is proportional to omega square, right? Omega is nothing but N, right? N is proportional to F. This is the relation which we do have already, isn't it? So what I can say now, W is directly proportional to F square. So any change in the power or any change in the kinetic energy, is going to affect your frequency. So now, assuming that there is a change in the kinetic energy because of change of these two things, assuming that there is a change in kinetic energy, and this has led to some change in frequency. Okay. So let the change in frequency be delta F. This will lead to new frequency. What is the new frequency now, guys? Initially F0. Now it is delta F. So the new frequency is F0 plus delta F. And I'll consider let the kinetic energy be W. I am not mentioning not here. Delta, which is equal to WKE0 plus delta WK. Okay. This is my new kinetic energy. So this is my new frequency, this is my new kinetic energy. So how to represent these two? How to relate these? How to relate these? WKE, this is a new value. By the old value is K0. This is going to be F plus delta F, F0 plus delta F by F0. This is whole square, isn't it? Hence, why I have come to this conclusion? Why? Because W is proportional to F square. I am employing this particular. Now, I'm gonna this is 1 plus delta F by F naught whole square, isn't it? Normally this larger term will be neglected. So approximately, because when compared to the frequency, it will be somewhere around 50 hertz. You take a normal frequency, this will be a change in frequency will be somewhere around 1. So if you take this particular term, 1 square by 50 square, it is 1 by 2500. It goes to somewhere around 5th decimal. So I'm going to neglect this one since it is very, very small. So I will consider it as a this is my new kinetic energy, isn't it? Or I can write it as HPR, where H is my inertia constant, and this is my power rating, isn't it? This is my power rating in terms of megawatts or kilowatts. Now, what did I say to you? Any change in delta PG minus delta PD is gonna affect your rate of change in kinetic energy, isn't it? So now, rate of kinetic energy is given by d by dt of W K. This is equal to d by dt of H into PR to 1 plus 2 delta F by F naught. Right? Out of all these things, H is basically a constant, PR is also a constant, and isn't it? Now, in this one, this is 0 plus 2 by F naught into d by dt of delta. Only this term is going to be affected with the change in time. All other things, this is initial frequency, this is machine rating, this is inertia constant, all these are all constant, isn't it? Only this is going to vary with respect to time. So, my final expression is H by PR F naught into d by dt of delta F. This is the rate of kinetic energy. This is the first accounting. Okay. This is the first accounting. Now, I told you that it will be accommodated. The change in delta PG and delta PF is going to be accommodated in 2 ways. One is this rate of change of energy. The other one is, I hope you do remember this model. I'm going to erase this one. Okay. So this is the first thing. Just I'll keep it like this itself. The second thing is, normally what happens is, this is the second way of accounting delta PG minus delta PD. Normally what happens in your motor, as you are all electrical engineers, you know it very clearly, right? Now, normally, when there is a change in frequency, when there is any change in frequency, the motor load is also going to vary with respect to frequency. The motor load also varies with changes in frequency. Why? Because the load is normally sensitive to the frequency, even though the sensitivity is very, very low. But we'll consider this one also. So when there is a change in frequency, then automatically the motor load is also going to vary. So what is motor load? Load I have already mentioned. This is PD, right? This is going to be PD. Normally, the rate at which it changes, we will assume that the rate of change of load with respect to frequency is constant. Okay. అంటే ఏంటంటారన్నా నార్మల్ గా ఫ్రీక్వెన్సీ చేంజ్ అనుకుంటుంది. Let us suppose my machine is running at 50 kilowatts at 50 hertz. 50 kilohertz at 50 hertz. Normally, let us suppose 49.5 hertz అనుకుంటుంది. సో ఆటోమేటిక్గా నా పవర్ కూడా తగ్గిపోతుంది. బేసికల్గా let us suppose ఇది 49.9 kilowatts వస్తుంది. అదే ఇది 49కి వచ్చింది అనుకుందాం. It will move to 49.8 kilowatts like this. So normally when there is a change in frequency, the load also is going to vary. But the deviation will be very, very low. But I assume that the deviation is going to be constant. Okay, that is what I have written here. Normally the motor load also varies with respect to change in frequency. And I'll assume it as a smaller one. But anyway, I'll consider that rate of change of load with respect to frequency is going to be constant. Okay, so now if that is the case, why this is happening actually? Because there is a change in frequency. Why there is a change in frequency? Because there is change in Pg minus Pd. Okay. So now this accounting will be such that this is Pd by df into delta. Okay. This particular one, I'll consider it as B. This will be helpful for you in next problems. B. B is considered to be rate of change of load with respect to frequency. Okay, B into delta. So now, combining the two equations. What are the two equations? This is equation number 1. This is equation number 2. So delta Pg minus delta Pd, one, it is accounting for H into PR by F0 into d by dt of delta F plus d into delta. This is a time dependent equation. Okay. So now what I am doing is I am gonna divide this entire one with PR. PR is rating of the machine, isn't it? So why I am doing this? Just I want to make this equation a per unit equation, so which will be helpful for me. Dividing entire thing with PR. This will become per unit. This will become per unit. Here, PR will go. I think there must be a 2, right? I forgot 2 here. Please check it again. This is B per unit into delta. Okay. Now, say this is a differential equation. Better I employ Laplace transform for doing this one. Applying Laplace transform, what will this become? Delta Pg of S per unit minus delta Pd of S. This is also in per unit. Okay. All these are all in per unit. This is 2h by F0. This is a differentiation, right? So I will be getting S into delta F of S. This is B into delta F of S. Because only F is going to be the term. This is going to vary with respect to time. All the other things, H, F0, B, all these are all full. So that's why only for F I have considered. Since it's a derivative, H into delta F of S. This is delta F of S. So now I am going to subject delta f of s. This is delta f of s. Now, if you carefully see, the expression is 1 by b plus 2hs by f naught. 2h f into f naught into this is delta pg of s minus delta pd of s. Isn't it? 1 minute. This is the expression now. One minute. So now I am gonna modify this one in order to be a more meaningful mathematical model. Now, see here. This is delta f of s. So here I'm going to take it as 1 by b, dividing with b and side terms. Okay, this is going to be 2h by b into f naught into s into delta pg of s minus delta pd of s. This is the expression. Now, we can represent it easily in terms of control system. We can consider this one. Now, this can be employed as, I'll write it in the separate thing. I'll consider 1 by b as gain of this model, and I'll consider this one as time constant. I'm taking this one as PS because this is a power system, electrical power system, generator and load. So I have mentioned it as PS. Okay. So now this delta f of s. Now, carefully see, this delta f of s is equal to Ksg by 1 plus s into tau sg into delta Pg of s, which is coming from the turbine, minus delta PD of s, which is coming from the load. This is the model. Now, if you carefully, which means that I am having two inputs. One is delta PG of s, which is coming from the turbine. This is delta PD of s, isn't it? Now, Kg by 1 plus s into tau sg. Now, this is going to be my delta f of s. Okay, this is going to be my delta f of s. Now, we will have a mathematical modeling for this one now itself. Okay, and we will see how it is going to affect our normally. I'll give you the values also. Normally, what happens in case of when we are going to the MATLAB modeling, basically, you are having two constants here. One is KSC, the other one is tau sg, isn't it? Normally, the time constant, this generator is a very big thing. So normally the time constant will be very, very high. For turbine, I have taken it as some 2 to 2.5. But whereas for generator, it is very, 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 very big. So normally, So time constant will be very high. You can take it as somewhere around 10 to 100, even higher also, depending upon the size of the machine. Whereas KSG, if you see, it is 1 by B, isn't it? What is B actually? B is nothing but the rate of change of flow. Normally, what will be the rate of change of flow? Normally, it will be somewhere around 1%. So it is 0.0. So normally, it is 100. If it is 2%, then you will be getting 50. So normally, the range of KSG will be somewhere around 10 to 100. But normally, we will be taking it as 100. And it may be larger also. Whereas the time constant, it will be in the range of 10 to 100 because the machine is a little bit heavier one. Okay. Now, you will see the mathematical model of this one now. And before going for the mathematical model, I would like to draw the complete block diagram of the isolated power system now. Okay. Now, earlier we have done for speed governor. For the speed governor, what we have got? I hope you do remember. This was 1 by R, right? This was delta F of S plus minus, right? This was the speed governor. This was our speed governor. So what was the output of this one? Delta YE of this. Now this was being fed to the turbine, which used to have just only a transfer function. This was the transfer function which we have developed in our previous video lecture. And its output was delta PT of S. Now I am also considering it as delta PG of S. Anything is okay for me. And see, this is delta PG of S, isn't it? Here there is another component. What is that component? This is plus, this is minus. Delta PD of S is coming. What is this one? KPS by 1 plus S into 2PS. What is the output, guys? Delta F of S, isn't it? KPS, so this is delta PG of S. Delta PD is my another input. KC by 1 plus S into 2SD. Sorry, this is PS, okay. This is for the power system, right? Generator load model. So generator load model. Now, if you carefully see, this is delta F of S, which is to be fed back to the. Okay. Now, if you carefully see, this is the block diagram representation of isolated power system. Isolated power system, or in other words, you can call it as single area system. You can also call it as single area system. Okay. Now, before going further, any further, I would like to mention the things for you. Normally, what are the values? I will again repeat for you. Normally, I do have three gains here: KSG, KC, and KPS. And I do have right. I'm going to erase this one. Apart from this, what do I have? I do have R value here. And how many inputs are there for the system? There are two inputs. One is delta PC for the entire system. Delta PC is one input, which is manual power commands. The other one is delta PD of S. This is delta PD of S. This is demand, electric demand, which is automatic in nature. Because demand we don't control. Demand will be varying automatically. So this is a manual part, this is a demand. Okay. So normally KG and KT, they are chosen such that their product will be equal to 1. Their product will be equal to 1. They are chosen like that. If you choose it as 0.5, it will be taken as 2, such that they both combine to give you a common value. Normally KPS, which I have already mentioned, it is 1 by B. It will be of the range of 100. It will vary from 10 to whatever value which you take. Normally I take it as 100 in our problem. And time constant for this one, it will be very, very low. Normally the time constant has already been said in the first class, in the previous class. Normally the time constant will be very, very low for speed governor because it is not having any large mechanical part. Normally it will be taken as 0.5 or 0.4 or 0.3 like that. Turbine is a little bit heavier part when compared to this one, so I will take it as 2 seconds. Generator and load model, it is a little bit complex thing. So I will be taking it as 20. And R, I will be taking it as 3. So the ranges you can vary. Now let us see what is the response of the system. And these are the parameters which I'll be taking in the max. Now let's see how the frequency is going to change for a change in power command or for a change in power command. Okay. Now let's get back to the MATLAB modeling. For a quick change, I'm gonna immediately now I'm going to show you the MATLAB modeling of power system now, the generator load model. Okay, I'm going to share 1 minute. Okay, I have taken a new model now. So I'm considering the library browser. So what you need actually, you do need 2 inputs, right? You can find them in the sources. Yeah, I need 2 constants. Two inputs, and I also need a transfer function model, which I can find in the continuous block, right? And I may also need a summer. Yeah, this is a summer, and I'll be also needing a scope, isn't it? Now, if you carefully see. Yeah. Now, Now, if you see, this is gonna be my, yeah, what I'm doing, this is my G press, and this is my signal. This is my transfer function of my generator load model, isn't it? I have told you the power, the gain I can take it as, I'll take it as 100 as of now, and the time constant, it will be a larger value, so I'm taking it as 20. Okay, so what will be my output? My output will be change in f of s, right? So first of all, I feel that there is no change in demand. This is a change in demand, so I'll take it as just 0. Now let us see, let us simulate it for 1 second. For the first time, it will take a little bit amount of time for simulation, because normally MATLAB in its advanced version, it just goes for backupping of all the previous models. So first time simulation, it takes a little bit amount of time. Okay, now this is done. If you carefully see, it is continuously increasing. Why? Because the time constant is 20 seconds, which means it is going to take a large amount of time for uh, getting a response. Okay, for getting it into steady states. So that's why what I'll be doing is this time seconds is 20 seconds I have taken, right? Time constant. So I'll be going with 200 seconds. Okay, because normally for 5 time periods, for 5 time constants, I'll be getting a steady state value. Since I have taken as 20, at least I may need 100 seconds for getting a steady state value. Now I'll show you. I have done it for 200 seconds. I'll see. At 100 seconds, I'm gonna. This is a blind thing which you should remember when you're going for higher examinations. In interviews, they will ask you what is the significance of time constants, whether we should know the value of that. Yes, sir, time constants, if we know the time constant, we can say at what time it will settle. Say in this case, what was our time constant? 20 seconds, right? So I can approximately say that for 5 time constants, my value is going to settle. See, you can observe it here. At 100 seconds, it is settling now. Okay. See the response. The demand was 0. There was a 100% change in input, mechanical input. See the change in frequency, it is increasing 100 times. 100 times it is increasing, isn't it? So that is a problem of small change in just only 100%, 100% increase in that one. See how much it is changing. I have just mentioned it as 100%. 1 means 100%. So what is the change in frequency? It is 100 into 100. How much? 10,000 times it is increasing. 10,000. Now, let us suppose I assume that there is no change in the generation, but suddenly my demand has doubled, which means the percentage change is going to be 1, isn't it? There is a 100% increase, which means demand has doubled. Now let's see what is going to be my change in frequency. See my change in frequencies. What is my change in frequency? 100 into, this is change in frequency is 100, isn't it? This is the problem. 100 into 100%, which means 10,000%, there is a change in my frequency. Now, what is significance of time constant? I will show you again. See, if I reduce a time constant, let us suppose if I take it as 10, what happens? Now my signal is settling down at 100 seconds, right? Now what happens? You see, I have just changed it to 10. See, time has reduced it to half because 10 is there 5 times, so 50 seconds I will be getting the settling value. Now, if you see, if I change the gain, change it to 50. If I run it, see, now it is 100. Now, so there is an impact of gain and also time constant on my output waveform. So you should choose them wisely. Now what we will do, we will combine this generator load model, speed governor model and turbine model. So now I'm gonna copy this one. Okay, I'll take a new one. Okay, yeah. I'll take a new one for you, and we will start from the basic. Yeah, how many? If you have seen this last picture which I have drawn on the board, how many inputs we do need? We do need two inputs. What are those two inputs? One is a manual power command, isn't it? Of S. What is the other one? This is going to be D of S. One is a manual power command. The other one is a automatic change in demand. This is manual power commands. If I need to change the frequency, I can give a signal here manually, or else the speed is going to automatically change when there is a change in system load. So these two are the things. Apart from this, what do I need? I need three blocks. One is for speed governor, the other one is for turbine, the other one is for generator load model, right? And apart from this, there is a gain which is represented by 1 by R in the speed governor model. Apart from this, to see the final output, I need my scope. These are the things which I need to have. Okay. And apart from this, I do need, right, two summers, isn't it? This is one summer. I can copy the same. Yeah. Now, what is this one? This is speed governor transfer function, isn't it? What is this one? This is turbine model, isn't it? What is this one? This is generator and load, isn't it? Now, speed governor is fed to turbine, and from turbine, there must be a summer, right? This is my summer because the PD will come into picture now. This is my frequency, change in frequency, isn't it? What is this one? This is, these all represent changes, okay? And what is this one? This is EG of S, isn't it? What is this one, guys? This is YE of S, change in setting of point E in the linkage mechanism. Now, see, this is a normal scope which gives you a change in frequency, but if you want to have a visualization of all these three things, I'm going to keep you another scope with three inputs. The first one is going to be manual power commands. The second one is going to be automatic change in demand. The third one is going to be change in output. So two inputs changes, and the third one is change in outputs. Now let's see. I'm going to run that. And if first one is gain of speed governor, I'm taking it as 0.4. You can take anything somewhere less than 1, okay? And this one I'm going to take it as 0.5 because its value is very low. Okay, I'll do one thing. I'll take it as 0.5. I'll take it as, because if it is 0.5, I can directly keep it as 2 here, right? So that they both will combine to form a 1 value. Here I can go with 2. This is the time constant, and for this one normally I'll be choosing a larger value. I can go with 50 or I can go with 100. Okay, for your sake I'll go with 100, and the time constant also will be very, very large. This will take it as 20. Okay, now this is 1 by r, isn't it? R normally speed regulation will be somewhere around 2 to 5%. Sometimes for worst case it will go up to 10%, but I'll take it as a random value of 3%. Okay. Now this is a change in manual power commands, assuming that I don't want to change manually, so I'll keep it as 0, and assume that there is a change, small change in the demand, and I'll take it as 0.1 per unit. It has changed by 10%. Okay, the demand has changed by 10% positively, plus 0.1, which means demand has increased. So what must happen to the frequency? The frequency must drop down. So let's see whether the frequency has dropped or not. Sorry, I'll keep it as 3. Yeah. I think this must be a negative. Yeah, if you see, this is the first one is the delta PC of S. This is delta PD of S. That is 0, isn't it? If you carefully see, manual power command is 0. There is a automatic demand is 0.1, which is 10%. See the change in frequency, it is continuously varying. So still it is varying because you have chosen a 20 as a time constant for generator load model. You are simulating only for 10. So I'll go with 150, which is 5 times larger than the larger value of the time constant. Okay. Let's look at this one. Have you got it now? See, there is a change in frequency, varying, wherein the frequency is fluctuating. See, and finally it is settling down at somewhere around 50 seconds. See the final value here. What is the final value? It is minus 0.3, which means it is decreasing by 30%. Minus 0.3. What is the change in frequency? Minus 0.3 per unit. Okay. I hope you have understood now. Okay. How to compute the change in frequency. So just because there is a change in demand, see there is a huge change in frequency. Nobody wants to have this change in frequency, isn't it? Everybody wants to control the frequency. Everybody wants to maintain the frequency constant. So I will show you. Now, since how much there is a change, that is 30%, which is caused by 10% change in demand. What I should do? My steady state change, there must be no change in frequency, which means that it must lie down at 0. But here there is a huge drop here, right? So what I should do? Since there is a drop in frequency, to improve the frequency, what I should do? I must increase this value. So this is a positive thing, positive input, right? So I must give it as some 0.1. Let's check if it is going to work. 0.1 for 10% change in demand, 10% change in steam. Am I going to get it near to 0? Yes, I'm going to get near to 0, isn't it? But is it really possible to vary for us manually all the time? No, it is not going to be possible, because this is going to change very rigorously with respect to time. I'm not going to be there all the time to settle it down.
See how much time it is taking for settling down also. It is taking nearly somewhere around 50 seconds. So I am not, and plus additionally I am not going to be there for it to vary all the time. So that's fine. I am going to use a controller. You might have studied about controllers, isn't it? So nobody wants a manual input here. Instead, what they will be doing is they will be employing an integral controller. You know what is an integral controller is? You know that? I'm gonna employ an integral controller here. Okay. What is integral controller? 1 by s, right? So I'm gonna choose a negative integral action, which will act as a feedback for me. Now I'll show it to you. What I'm doing, and just I'm removing the manual command. To remove the manual command, just what I'm employing, I'm just including an integral controller into the system. Now let's see. Mm, 1 minute. I think I'll choose a very low value. Just give me I'll make it as yeah. Now it's coming down. See now what I have done. I have chosen just an integral controller. Just I have before you itself I have changed the value of gain of the controller. This is an integral controller. Already there is a proportional constant going as a feedback. This is called as P controller. Now what I have done to remove the manual input, what I have done, I have added an integral controller. Now this is a P controller adding a feedback. This is I controller, isn't it? Both combinedly they form as PI controller. So what is the effect of PI controller, guys? What is the effect of PI controller? See the final value. What is the final value? It is settling down very fastly. Now, if you want, I will show you now. I'll show you in the same graph now. Okay, I'm gonna reduce the shape of this one. Draw the same thing here. I'll remove the controller here. Okay, I'll just keep as normal thing which was there earlier. What was there earlier? Earlier they used it to be earlier they used it to be PG office, right? So I'm gonna keep this one. Just I'm gonna keep as a 0 here. Okay. Now this is without controller. This is without controller. The bottom one is without controller. The top one is with controller. If you carefully see, okay. Now I hope you can see this one. Now I'm gonna compare this two outputs for you. This is the output of the bottom one. This is the output of the top one. Now I'm going to simulate this one for you. This is the bottom one. Yellow one is the bottom one. This is without PI controller. What is the top one? This is with PI controller. With PI controller, if you can carefully see, the oscillations are dying down and the steady state value is 0. So what you can say, the PI controllers can reduce the steady state errors, isn't it? Even though it is taking large amount of time for settling, but the final steady state value is in your limits. That is the advantage of using PI controller. Okay, and this is the response of your single area system with integral controller. Okay, tomorrow we will see theoretically how this is going to affect, or at least I'll provide the notes for you. Okay, so what you should do, what is the effect of PI controller? The PI controller is gonna reduce my steady state errors. Okay, that's it for today, guys. Thank you for joining.